Today we're going to be testing the timing accuracy of the bolt. Time is of course important when you're collecting data, and the bolt has two mechanisms for recording time. It has what's known as a real-time clock that allows it to keep track of the time of day and accurately timestamp information to the second. And the heart of that is the real-time clock that produces a 1 pulse per second output that is then fed into the rest of the bolt circuitry. The other aspect we'll be testing is the bolt's ability to phase lock to the power line frequency, because some of the timing that the bolt performs is in terms of counting 60 Hz cycles. So its power line tracking is another time aspect that we'll be testing here at room temperature and over temperature. And to test the bolt's accuracy, we have some equipment from the PMI test lab. We have a 3-phase power supply, of course, supplying stable voltage to the bolt. And then we have a rubidium atomic clock. This provides a very accurate time reference for the frequency counter. So this atomic clock is based on rubidium atomic oscillations, and that produces a 10 megahertz reference clock that is accurate to 10 to the minus 9 or better accuracy. So this feeds into the frequency counter. The counter is accurate as a standalone device, but it's even more accurate when it is tied to the frequency standard. So we have an accurate time base here to measure another clock like the bolt. So to do that, we put the bolt in the environmental chamber, and we are looking at internal signals in the bolt. The real-time clock pulse per second is not a signal that's brought out to the outside. So we have signals that go into the digital circuitry of the bolt, and we're connecting to these signals with the oscilloscope. And so we can look at them on the scope and also put them into the frequency counter to measure at the circuit level error 1 pulse per second output. So we're going to be doing this at room temperature and then use the chamber to go hot and cold to make sure it's accurate at the extremes of temperature. So the bolt is inside the chamber. So we have the oscilloscope that's looking at the pulse per second, and we're also running it into the frequency counter. So on the scope, you can see this is a negative going pulse, and this comes out from the real-time clock inside the bolt once per second. With the scope, we're going to look at drift over temperature. We'll do that after we make the room temperature measure. So we have the pulse per second going into channel 1 of the scope and teed off to go into channel 1 of the counter. And the frequency counter is measuring the period of this 1 pulse per second. And here it's reading 1.000001397 seconds. So let's put that into our sheet. That gives us an error of 1.3 parts per million. That's a very small amount of error. That's a few seconds per month. So that's a very accurate real-time clock. A typical real-time clock is on the order plus or minus 50 parts per million over its entire temperature range. So we can set the scope to show us that drift over time. Here we're triggering on the negative going edge of the second. So you can see the negative going edge of the pulse. This is the pulse 1 second after the trigger. So the first pulse was way over here. Now we are looking at the 1 second later pulse. So now if there's any drift at all over temperature, we'll see this slowly move back and forth. So we've seen that the bolt is very accurate at room temperature. But let's check to see if there's any drift at hot or cold temperatures. The second test that we're going to do at all the temperatures is measuring its line frequency phase lock ability. Here we've set the AC power supply to exactly 60 Hertz, and the bolt is synchronized into that, and that measurement output is accessible through PQ Canvas. Here I have a live connection through Wi-Fi. The bolt is joined to Wi-Fi right now. I'm connected to PQ Canvas, and I'm looking at its real-time frequency display, and we can see it at 60.003 Hertz. Let's take a look at the frequency counter, and we're measuring 60.0028 Hertz. That gives us about 2.3 parts per million difference. Extremely accurate timing at room temperature for the 60 Hertz phase lock. So now let's go cold in temperature and see if there's any drift in the bolt and either of its time measurements. So we'll set the chamber down to minus 40 Celsius, and we'll give that a good time to soak and reach its final temperature, and then we'll make these measurements again. Okay, now we're at minus 40 degrees Celsius. We're at the lower end of the bolt's operating range, and we can see on the scope that we see a little bit of drift. We'll turn on the cursors. That's about 8 microseconds or so. We look on the counter. We're at 99.9618 hertz or millihertz. So let's type that into the sheet. That's about 38 parts per million difference, which is still well within a plus or minus 50 ppm of a good real-time clock. And if you look at the frequency, Uh, the output of the supply is unchanged. We're at 6.002.0027293, and that still matches a peak of canvas of 60.0003. So that's really unchanged. So that's still 2 to 3 parts per million measurement accuracy on the line frequency. Okay, now we've let the bolt soak at hot temperature. Let's take a look at the real-time clock accuracy. We can see it on the frequency meter. We're reading 0.99962 milliseconds. That gives us a difference of 38 parts per million, so roughly the same drift as we had cold. Still well within good real-time clock performance. And if we take a look at the scope, we can verify the same measurement. We have about 37 microseconds difference, so that corroborates the frequency measurement here with the frequency meter. We have the AC power supply still putting out that same frequency. So we're still at 60.003 roughly, well under 2 parts per million difference. So the bolt is very accurate and shows absolutely no drift on power line frequency phase locking, and the real-time clock is well within its spec, should provide good accuracy over time.